I'm Zerda, I'm the department head for physics. I'd like to welcome some of our guests here, President Cruzado, Provost Botvin, Dean Ray, Vice President Renee Pera, all visiting here to hear what I think is going to be one of the Nobel Prizes in physics in the next couple of years. And the one who's going to tell us about it is our own professor of physics, Neil Cornish.
All right, it's an exciting day. Back in August last year, we had our kickoff workshop for the Extreme Gravity Institute. And a short time later, on September 14th, the universe sent us a message. It was very fitting. So we had a gravitational wave arrive at 3 a.m. in the morning on September the 14th, so just a couple of weeks after our workshop. So it's a great way to kick off our Extreme Gravity Institute. So this is the title of the paper that appeared online today in Physical Review Letters. It got so many hits in the first few seconds when it went live that it crashed the server for the journal. So this story is more than 40 years in the making. Two of the founders of the experiment that made the detection, Ray Weiss at MIT, Kip Thorne at Caltech. There was also another person at Caltech, Ronald Drever, who was, these are the three co-creators. I know Ray and Kip very well, so I have their photos up here. I'm hoping very much that these gentlemen get rewarded for their visionary efforts with a Nobel Prize sometime in the next year or so. It's a story 40 years in the making. That's Ray and Kip back when they were first proposing LIGO. Here's Ray and Kip today. Perseverance is important in this game. For about the last 5 years, my son, who's in the audience, would ask me about once or twice a week as I was walking across Cooper Park to school, he'd say, "Daddy, have you found those waves yet?" And finally, on the 15th of September last year, when I was looking at the first results and our analysis of the wave, I said to him, "Well, don't tell your friends," not that it's going to leak, but I think we might have found those waves. So he was one of the first people to know. So the story began even earlier than that, in a long time ago, in a galaxy far, far away. And this happened. That was actually slowed down. I'll show an even slower version. This is what it would look like if you were about a few thousand kilometers away from the black holes that we observed the signal from. So here are the black holes, and here's the stars you would see behind them. And the image of that star is distorted because the light from the stars is bent. Distortions of gravity due to these black holes is warping the space-time. So it's starlight's, the path of the light of the stars gets warped. So you'd see this crazy pattern happening. These two black holes, as they come in, get closer and closer to each other. They finally merge to form a single black hole. And then it sort of settles down. While all of this is happening, gravitational waves are coming out. But this would be the view you would have seen if you were just a few thousand kilometers away. Now, this actually happened more like 1.3 billion light years away. So how did we detect this signal? This certainly isn't what we've seen. This is a computer simulation of what it would have looked like up close. Lag on my. So here we are. And here's the galaxy far, far away. It's somewhere over here. We don't know exactly. We can't locate it very well, but somewhere down this way. About 1.3 billion light years away. And these are superclusters of galaxies, but we can't pinpoint it to any particular galaxy or any particular supercluster, but somewhere down here. And to measure those signals, we used this. This is one of the detectors closest to us. This is the one in Hanford, Washington. There's the lasers are there. This is a 4-kilometer concrete pipe that houses the beam tube. And here's the twin detector down in Livingston, Louisiana. You can see the swamp here. It has alligators in it, that sort of thing. And so we use these two detectors, the one in Hanford, Washington, and the one in Livingston, Louisiana, essentially as our ears on the universe to sense these vibrations. These are the most sensitive measuring devices ever built by man. And what we're looking for, Einstein's theory of gravity tells us that gravity is not so much a force, but a manifestation of warpage of space-time. So something like the sun warps the fabric of space-time, and then something like the Earth just tries to follow the straightest path it can, sort of rolls around in this bowl. So there's not so much a force of gravity, but it actually is a warping of space-time. If you then have, say, two black holes, or maybe two neutron stars, some other compact objects orbiting around each other, they give off gravitational waves that causes them to spiral in. It raises these ripples, and these ripples then head out into the universe, a bit like dropping a rock into a pond, or here's raindrops falling on a pond, and you get these ripples going out. So then we're trying to detect these ripples, not in sound or in water, but ripples in actually space itself, space stretching in and out. So here's a vastly exaggerated and also slowed down image. If gravitational waves were far stronger, if gravity was a stronger force, this is what it would have been like when the gravitational wave went past the Earth. I'm actually going to go back to that just for a second. Let's try that again. This is actually, notice that the waves are first hitting, this is the site down in Louisiana, here's the site in Hanford, Washington. The waves hit first here, and then they're about 7 milliseconds apart, and that's one of the things we use to figure out where in the sky they came from. Now, the warping of space that occurs is not nearly that strong. This is what it looks like if the gravitational wave was going into the screen. You've got the warping. If you just had some masses floating free in space, they would actually go through this squeezing in and out pattern. And there's two polarizations. The other one goes at 45 degrees. If you look at that as a cartoon where time is heading across this way, you can then imagine how you might detect them, because if we could somehow measure the distance, say, between this mass, and this one and this one, just like that L-shaped setup we have for the detectors, as the gravitational wave goes through, this arm would get longer than this one, and then at a later point in the cycle, this arm would be longer. So if we can measure this fractional change in the length, which is called a strain, then we would be able to detect the gravitational waves just by the stretching in and out of space-time. Now, the way we do that, because it turns out the stretching is very small, is we actually use lasers as rulers. So we have a laser, we run it through a beam splitter that sends half the light down to one mirror, sends the other light to another mirror, the light bounces back, recombines, and then we have a viewing screen, which is actually a photodiode pickup. And if the distance along this arm differs from the distance along this arm by a half wavelength, the waves meet crest to trough, and they cancel out and you get nothing. If it's just a half wavelength longer, if it's exactly the same distance or any multiple of a wavelength, they come back crest to crest, trough to trough, and you get constructive interference. LIGO sits very close to the destructive interference with almost no light coming through, and then just if anything comes along and disturbs the system, light starts coming through, and so we can measure very minute changes in the distance. How minute's kind of incredible. The wave that we detected produced a fractional change in the length, which is a strain, of parts in 10 to the minus 21. And over 4 kilometers, that corresponds to a shift of 10 to the minus 3 Fermis. Now, a Fermi, here's an angstrom. This is the size of an atom. That's 100,000 Fermis. Here's a Fermi. That's the nucleus of an atom. So we're sensing the distance between masses 4 kilometers apart to, in fact, this instrument can do 10 times better. It can do 1/10,000th the width of a nucleus of an atom. It's very hard to get your head around that. It's equivalent to measuring the distance, tracking the distance to Proxima Centauri, the closest star, which is still a decent distance away from us, to the width of a human hair. Right? So this is an absolutely phenomenal feat of engineering to build a detector with the sensitivity to measure these minute changes. Just to put you into perspective, another way of viewing this, the wave as it came through change the distance between the Earth and the Sun, wobbling back and forward by the width of an atom, okay? So these are incredibly tiny disturbances that we're trying to detect. Here is a computer simulation produced by a Caltech Cornell group showing the black holes. You can see this is the timestamp, so it's massively slowed down. It gets even slower in a moment to show the details. Here are the black holes, and they're warping the curvature of space as they spiral in towards each other. And the gravitational waves are carrying away energy and angular momentum from the system. Here's the wave pattern that they're producing. So what we've got is the waves going along. It's going up in amplitude, and you can also see that the crests are getting closer together, so it's also going up in pitch. Here we've slowed down time even more to see the dramatic final moments as the two black holes come together to merge. And this is the merger portion of the waveform. It's frozen here just to show the extreme, just at the moment that they start to form a single black hole, and then that single black hole then rings down, gets rid of its final distortions, and those waves propagate out, and those are the waves that we then detect 1.3 billion years later. So this was the group that notice that they also have the extreme spacetimes. All right, here is the first figure from that physical review letter that appeared today and crashed the server. Here's the output of the two detectors. It's kind of noisy. This is being put through a filter, so it's going to raise the features up a little bit. This second panel here, myself and my group here, I have two members of my group who work on LIGO are in the audience. Meg Milhouse was actually running the analysis at the time of the event. And this gray shaded thing, which says a wavelet reconstruction, which is this one here, this is the, this analysis was developed here by myself and one of my former graduate students, Tyson Littenberg, building on work I did with another graduate student of mine, Paul Baker, and now Meg Milhouse is further developing this with me. We actually have in the audience today tomorrow's colloquium speaker in the physics department, Chris Pankow, who's a postdoc at Northwestern, and Chris actually was on the review team that reviewed this analysis, so we thank Chris for helping out in that. So we're very proud to actually have our analysis, which was able to reconstruct the wave without any assumptions that it was a wave that was predicted by Einstein's theory. So we can do a model-free reconstruction of the wave. The other lines we can see here are the ones that actually use so-called templates, which are based off solutions to Einstein's theory, and also the blue one is what you get from a numerical relativity simulation, which I was showing you earlier. And so what's really cool is this gray band, which is what we were able to reconstruct without any assumptions, matches so beautifully with the predictions of Einstein's theory. So here's the actual output from the detector for the 2 seconds surrounding the event. This is where the event happened. And it turns out that these waves actually are in the human auditory range. So without any modification, I can just take that and play it. And what you're going to hear, it's noisy, so this is the detector noise, this is the event, and then I'll play it the cleaned up version that we get by processing it through the software that we developed. Okay, so here's the raw one. And it's sort of loud, and that little thump was the gravitational wave. And then what we're able to do is extract the part of those two signals that's coherent between the two detectors. So this is what we extracted. We get rid of all the noise. And so this is the so-called phase wave algorithm that we developed here at MSU. And then you can play it again, and that's the gravitational wave going. So that's it. That's the little tweet that the black hole sent out, congratulating us on establishing this extreme gravity institute. So I'm going to play it one more time. So this was many, many years of work to make the software to do this. So. A good resounding thump. The frequencies here this wave is sweeping up from around about 40 hertz is when we first started picking it up in the detector band, up to around 250 hertz. So it's at the low end. That's very bassy kind of sound. That's why we're getting that very thump kind of sound, which means that they're quite heavy black holes. All right. This is just to advertise further what we do here. So we actually reconstruct the wave out of a sum of wavelets. So in this top panel, each of these different colors is a wavelet. Wavelet means just small wave, so it's just a little wave packet. And we reconstruct it as a sum of little wave packets. You sum those all together and you get this pattern here, and that's how we pull the signal out from the data, is using this combination of wavelets. So that's the MSU analysis. And you can compare that to an analysis that uses predictions from using Einstein's theory of gravity and actually predicting what the wave should look like. And we have a 94% or better match between the two types of analysis. So one that actually uses the analysis, uses Einstein's theory, and one that just looks for any kind of wave. We've got this beautiful agreement between the two. The mismatch, the fact that it's not 100%, is exactly what we'd expect. We don't expect a perfect match. So this is very consistent. All right, so we detect gravitational waves. Gravitational waves, Einstein published his theory of gravity in 1915. He published another paper then in 1916 where he predicted the existence of gravitational waves. And we've since been able to simulate black hole mergers and things like that on supercomputers, so we can compare very detailed predictions using Einstein's theory of gravity and see how much does it actually look like what we record in the data. Were these waves consistent with general relativity? So this here shows the data with the gravitational wave in, and then you notice it disappears. That's when we use the best fit model to subtract away the signal. And in a paper that Nico Yunus, Laura Sampson, who's in the audience over here, and I published back in 2011, we produced this formula here, don't have to worry about the details, that said that the residual signal to noise would be related to the detected signal to noise and the so-called fitting fact, which is a measure of agreement with the model. And from the measurements we made, this actually shows that this signal agrees with Einstein at least at the 96% level. We're not finding any departure from Einstein's theory, but we can say that it's consistent at least to the 96% level. I mean, we have no reason to think that it's not 100% consistent, but just the data is noisy, so this is the best we can do. So we know that Einstein was at least 96% right. We can do a more detailed analysis where you can actually solve Einstein's theory order by order and an expansion in the velocity of the system divided by the speed of light. Now back in 2010, Nico and Scott Hughes published these bounds on these departures from general relativity using data from a binary pulsar system. So these were the bounds that they published back then. Because that binary pulsar system has an orbit that's far slower, it doesn't really give you a very good measurement of these higher order terms. It's only going at about 1,000th the speed of light, whereas the black holes, when they finally merged, were going at about half the speed of light, right? So if you want to try and measure, you take something 1,000th and raise it to the power 7, you don't have a very good bound. But now we've got something that's going about half the speed of light. These are the upper bounds. So now, with this gravitational wave, which has a name, we call it gravitational wave 150914, meaning 2015, 9th month, 14th day. Okay, so that's its designation. Normally, like this pulsar, its designation actually is its sky location. Here we designate gravitational waves by when they arrived. Okay, so the bounds are significantly better now that we have this far more relativistic system. But Nico and Laura and I worked on using this kind of, we actually predicted that this is the kind of bounds we could place on general relativity if we could ever detect a gravitational wave like this. So we've published a lot of papers where we actually have graphs that look just like this, but we were using fake data for this part. Now we have the real data, and so we've been able to apply these sort of bounds to using real data. These are the physical parameters of the system. So there were two black holes that merged. These are the error bars we have on it. So one of them was roughly 36 times the mass of the sun. The other one was 29 times the mass of the sun. You add those two numbers together and you get 65. The final black hole had a mass of 62 times the mass of the sun. So we lost 3 solar masses. They actually went out in gravitational waves. 3 solar masses worth of energy came out. The final black hole is spinning at, its spins are measured between 0 and 1, and so it's spinning at like 70% of maximum. It was, like I said, 410 megaparsecs away, which multiply that by, into light years, that's about 1.3 billion light years, and that's that's a redshift of how far away the universe was, another measure. So those are some of the physical parameters. Here is roughly where we think it was in the sky. With gravitational waves, just like with hearing, it's very difficult to localize things. We get a lot of the localization just from time of arrival, right? So that kind of restricts it to some ring on the sky, but then we also, just like our ears, that we have a sort of an antenna pattern which narrows it down, but this sort of confidence region covers about 1% of the sky. This is the view from the southern hemisphere. Here's the Large Magellanic Cloud, Small Magellanic Cloud. It's way back past all of those, but those are the nearby. This is what it would, this is the sky looking up from the South Atlantic at the region where we think the wave came from. In the future, we hope to be able to pin down the location of these signals much better because we only had 2 detectors running. In the future, we hope to have, I'll get to this later, more like 6 detectors running, and then we'll go pinpoint it much more accurately. So for the moment, we can just sort of say it's sort of over there somewhere. If you're wondering, how do we measure the mass and spin of the black holes? Well, here's what the signal looks like in a, using the best fit parameters we got. Now, if we were to change the mass by a factor of 2, the final mass, that increases the frequency by pretty much a factor of 2. So you see the wiggles don't match anymore. It was roughly a 1-to-1 mass ratio. If we change the mass ratio to 4-to-1, it doesn't really match anymore. If we change the spins of the original black holes, it actually doesn't match. So what we do is we tweak all these parameters. We actually have a computer do it because we have 15 parameters we need to try out. And so the computer just goes through trying out all these different parameters, looking for the ones that give the best fit, and then the range of those parameters that actually are consistent with the signal, that kind of gives us the error bars on our measurements, right? So it's by this pattern matching comparison of comparing the model to the data is actually how we measure the physical parameters. And it's a bit like with speech. Your brain has a template in it for what an A sounds like, what an E sounds like. And so when you're listening to speech, your brain is doing this pattern matching. And so we've figured out the language of black holes. And so we're able, when we hear a black hole talking to us, like we've now done, we can actually say, okay, the black hole's telling us it has this mass and this spin. So we can decode the message that black holes deliver. What's really cool is when you compare all of the known stellar remnant black holes, the ones from collapsed stars, these measurements here aren't very reliable, but from the ones in our galaxy, the known black holes, we've never seen a binary black hole before. We've never seen 2 black holes together. These are black holes with other stars as their companions that aren't black holes. All the previous black holes that have been measured with any confident masses all had masses somewhere between about 5 and 15 times the mass of the sun. The 2 black holes that merged are up here. It's a completely different class of black holes. These formed from a very different way from these black holes. You cannot form big black holes like this from regular stars. These have to be a very special kind of star that forms black holes this big. So we have discovered not just the first ever binary system of black holes, but we've also discovered a new type of black hole in a mass range that no one's ever seen before, which is really exciting. Of course, the one that merged was then 62 solar masses, so it's sort of off the screen. There's some theories about where do these heavy black holes come from. One of the most exciting, I don't necessarily think it's the most likely, but one of the most exciting is it could actually be from the collapse of the first stars in the universe. the first stars in the universe were much more massive than the sun. They typically had masses, we think, hundreds to, like at least maybe even 300 times the mass of the sun. And when they collapse, they form, a lot of the outer layers get blown off. In fact, a lot of the outer layers of those first stars produced a lot of the iron that's in your blood, right? So they were very good at producing iron. But the part that didn't get blown off and become part of our blood, if it collapsed to form black holes, so these could be stragglers from this first population of stars. Another thing is they could be forming in dense stellar clusters where the black holes sink to the middle and undergo many mergers. So these could be the result of not the first merger, but like subsequent mergers. There's all sorts of other ideas about very tightly bound massive stars. Basically, they have to be very different from the sun. The sun has way too much pollution from other elements other than hydrogen and helium to produce anything like this. So this is an interesting question that astrophysicists are going to be puzzling about now, is where did these heavy black holes come from? So we've already got our first surprise. We've discovered a new type of black hole. That means we've got work to do figuring out how they formed in the first place. Okay, a few other, one of the really cool things, the connection to Montana here, the area of the event horizon of the merged black hole, this is the formula, its surface area, when you calculate it, is 370,000 kilometers squared, right? The surface area of Montana is 380,000 kilometers squared, and certainly within the error bars we have on this area, and I would say the error bars on the area of Montana, it's mountainous. Like, how does someone figure out the area of Montana, right? But I would say that to within the error bars, this black hole has exactly the same area as Montana, which is pretty cool. Again, showing that this black hole was sending us a message of congratulations for establishing the Extreme Gravity Institute here in Montana. So, now, there's some differences. The black hole is rotating 100 times per second, whereas Montana rotates once per day. So, so this black hole is still rotating right now at 100 times per second. So it's not completely the same. Now, I've been telling you about how weak gravity is, that it's actually stretched space between us and the sun by the width of an atom, right? So that makes gravity seem pretty puny. But is gravity really that puny? Well, if you actually just measure it in the relative strength against the other four forces, the electromagnetic force, the strong nuclear force, or the weak nuclear force, it seems kind of puny in that sense. But these waves transmitted a vast amount of energy. So as a great physicist once said,
"You don't know the power of the dark side."
So let's talk a little bit about energy scales. And this is one of my favorites. Someone even wrote a poem about this that was presented at Nico's Physics and Poetry. Oh, you'll like this. Okay, so to get our head around the energy scales involved, thermonuclear weapon ever detonated. It was a Russian thermonuclear device, around 50 megaton yield. And that detonation converted about 3 kilograms of matter into energy. So, so that's equivalent to vaporizing a cat, okay? So that is my unit of energy, is 1 cat. So in terms of this unit, let's Okay, the destruction of Alderaan. That's a million billion cats. If you want to figure out how to calculate this, you just calculate the gravitational binding energy of the Earth. I think Alderaan's pretty much the same as the Earth. And that's what it equates to. The energy to destroy a planet is a million billion cats. Now, what about this black hole merger? The energy released from that black hole merger was a billion billion trillion cats. So as a great physicist once said,
The ability to destroy a planet is insignificant next to the power of the Force.
So this event is the most energetic event ever observed in the universe. It outshone every star in every galaxy in the universe by a factor of 50, right? The combined output of everything in the universe. This vastly exceeded its energy output. And as a reminder, it's the same as taking 3 suns and turning them completely into energy, right? 3 solar masses of pure energy. So gravity's not that puny, very powerful. Okay, so just to finish up, this is the beginning of gravitational wave astronomy, not the end. Currently, we have the detectors in Hanford and Livingston. Later this year, when we embark on the next observing run, we'll be joined by the Virgo Detector, which is just outside of Pisa in Italy. We have a smaller detector that wasn't running at the time of the event, which is operational, the Geo Detector in Germany. We hope in the future to place one of the LIGO detectors. We have a spare one. Well, we used to have 2 in the Hanford site, but we figured it was kind of silly to have 2 at the same place because they can have common noise sources, and also if we want to actually figure out where things are on the sky, it's better if they're separated so we can triangulate. So we're going to put one of those in India, and the Japanese are building one down in the Kemiokande mine. So going forward, certainly starting the end of this year, we'll have another big detector joining the network, and in by the end of the, a little early into next decade, we'll have, well, this one should be ready by the end of the decade as well, and then LIGO India earlier next decade. So we're going to be able to so this is really just the beginning. We actually think that based on our projected event rates from what we've just measured, we're probably going to see, during the next observing run, assuming that the sensitivity gets to where we're hoping to be, we could see up to maybe another 10 events or so in the next one. And then for the observing run after that, more like 50 or so. So this is just the beginning. These are going to become sort of commonplace. And then further into the future, we want to cover the entire gravitational wave spectrum. So these ground-based interferometers I was telling you about, they're operating up at these higher frequencies. I'm also involved in a project using pulsar timing, which is looking at much lower frequencies. And we also hope to put a detector in space to cover this mid-region. And we can also look for gravitational waves that have billion-year periods, looking for imprints in the microwave background. So this is really the dawn of gravitational wave astronomy. It's the beginning of it's the end of the search for the first signal, but it's really just the dawn of a whole new form of astronomy. And that's the end of my story. Thank you. Are there any questions? Yes.
So, you mentioned that this event is the most energetic we've ever seen. Could you compare it to a supernova, which I suppose is the previous most energetic event that we've seen?
supernova weren't the previous most energetic. That would be gamma ray bursts.
Okay.
So gamma ray bursts are still at least 1,000 times less powerful than this. So this is still dramatically larger than any energy release we've seen before. Renee?
Can we get one of these in Montana?
You know, it's funny you should ask that because when they were actually looking for places to site the detector, back when they were building these, Montana there was site studies done in Montana, and there were some pretty good sites in Montana. The advantage here is the government already owned the land. It's the Hanford Nuclear Reservation, and they also control the site because they have lots of nasty nuclear stuff there, so there's guards driving around. So Montana wasn't picked, and now because there's one in Hanford, Washington, which is it's too close. We're not going to stick one in Montana. We're going to go and put one in India. We want to be as far away as possible. We really wanted to put one in Australia, but the Australian government, it's one of those gifts like we were going to give them a free detector, but the problem is building the concrete tubes and the buildings and everything, siting it, and it costs about $140 million to site one of these things. So while the detector came from free, installing it was going to cost them about $140, $150 million, and they didn't feel like quite afford it at the time. So unfortunately, it's not going to go to Australia, it's going to go to India instead. Yes?
Are there any pairs of black holes that are closer that might happen, that might rattle our windows?
You know, to rattle our windows, no. I mean,
They're the close ones that have a bigger effect.
oh, absolutely. I mean, the closer they are, the bigger their effect. These are rare events, relatively rare events. So, but actually, let's see, what is it? We think that they probably occur somewhere in the universe. Do you remember, Laura? Was it once or twice, or Chris, once or twice an hour or something like that, or?
It's every 15 seconds, I thought.
Is it every 15 seconds? Yeah, so these are actually happening all the time, but you know, our detectors are only covering, it sounds like a long way to get out to 1 billion light years, but that's still a tiny fraction of the universe. So you're much more likely to see one far away because there's far more space out there. We hope to see some even closer, and we'll get a much bigger signal when we get one closer. So I would say in the next couple of years, we're going to see one closer than the one we just saw, but it's certainly not going to be rattling your windows. It'll be a much bigger signal than the one we got. But this was still pretty spectacular compared to, I mean, in our wildest dreams, we didn't think that the first one we found would be so spectacular. It was very, very bright.
How long has the current L1H1 array been operating, and how much observing time has led to this one event?
So the detectors were operating for several years in what we call the initial configuration, and then we tore them torn apart and completely rebuilt. We were going through a series of sort of tune-ups during last year, and we were just in our final tune-up, locking the detector, just about to start the official beginning of observations when the signal arrived. So it actually arrived a few days before the official start, but we already had the instrument up and running. We're doing the final calibrations and tests and whatever. So we just locked it in that mode and didn't touch it then. And so it had been running for a while, but sort of in this sort of warm-up mode. So we caught it right at the very beginning of the observation run. The papers we're publishing today, I think something like 12 papers we put out today, including the one that's accepted, the discovery paper. Those only cover the first part of this observing run, 16 days of, roughly 16, 17 days of coincident data. We have more in the can that we're still analyzing. So there'll be more, we'll have more results that we'll report at some later date, and we have to analyze that other data. So we decided just to kind of get this bit analyzed. We just took a chunk, analyzed it, get the papers out, And now we're going to work on the rest of the
So
data.
there's a
and-
finite probability that within the year, more winds will.
Yeah, so we've got more data to go, and we have, next, hopefully by around fall of this year, late summer, fall, we'll be back online again with greater sensitivity, and we'll run for several months, and hopefully with the Italian detector also going at that point. It's actually a joint Italian-French project, but it's sited in Italy. So at that point, we're hoping it becomes almost like commonplace. In fact, one of the conversations within the collaboration, the amount of work that we've done over the last few months on this, has been incredible. We cannot spend this much time on each one if we're getting 10 or 20 or 50, so we have to figure out how to do this a bit faster. Actually, I would like, before I take another question, if I could have we actually today have 4 of the authors of the paper in the room. So if I'd like, we have Chris Pankow from Northwestern, Laura Sampson, one of my former students, is Meg Millhouse. Meg was here at MSU, is one of my grad students currently. Meg was actually running the online analysis when the event came in. We actually had Gravity Group meeting on Monday, the day of the event came in that morning, and Meg said to me, "Did you see that? See that alert that came?" And I said, "Yeah, it looks pretty good." And we ran our analysis, and the next day we saw the waves, and I was like, that's when I said to James, I think we might have found those waves. So, so there's some other questions. I haven't. George.
Was this a one-time opportunity, or can the same event be detected again and again?
This is a one-time opportunity. Those black holes have merged. There's now, that black hole's just sitting there now, not doing very much. So it'll be other black holes merging and there's lots of other things we can detect. We're hoping to detect merging neutron stars, which will then allow us to probe the dense nuclear matter, like to understand how matter behaves at these extreme densities. So there's a whole class of signals that we now hope to detect. We hope to find lots more of these black holes. So but that particular system, it's gone. Yes.
So how can the collaboration be sure that the templates that they're using and the wavelet stacking, that there's not some error in there that the collaborators are choosing and not just reading the signal directly? It seems like you're choosing thousands of different templates and one of them sticks, and that's the signal that you choose. Like, what are the statistics in that?
Right, so what we also do is we assess how likely is it that something in the detectors might just randomly make a pattern that matches, because we are trying out lots and lots and lots of templates, right? So you might think, well, something's going to match that. The instrument does produce lots of little blips and whistles and things just from, we don't quite know what a lot of the time. So we assessed, we're able to assess that by looking at how often the blips are, and we can actually calculate then, and we do this thing of actually taking the data and artificially shifting it in time and repeating the analysis over and over again and just seeing what our random chance of just randomly getting things to be detected. And the significance of this event is greater than what we'd expect to happen randomly once every 200,000 years. We can't even actually assess the significance completely because it's so significant that it even kind of saturates our ability to assess. So it's probably, if you did this observation for maybe 1 million years, this might happen by accident. So that's why we're pretty confident that it's the real deal, because we're only observing for a few days. That's why it takes from September till to now to actually have the papers out, is because we spent a lot of time really checking that result to make sure it was, we weren't being fooled by something. So, but that's the part of the analysis. There's one right at the back, and then I'll get, yes?
Do gravitational waves propagate at the speed of light?
That is a really good question, and that is the prediction of Einstein's theory is that gravitational waves do propagate at the speed of light. Here we've not been able to test that exactly because we don't have, this event, as far as we know, didn't emit any kind of light at the same time. So the simplest way to test that, right, would be to see did the light signal arrive at the same time as the gravitational wave? There's other more technical things we can do. For example, if the particle that carries, the graviton, if it had a mass, then that would mean it would travel at less than the speed of light. We've been able to place bounds on the mass of the graviton using this event, but there are other ways that gravity could not travel at the speed of light that we're not able to test yet. That's something that we hope to do in the future, and it's something we'll be able to do more directly when we have something like 2 neutron stars merge, because then we can get a gamma ray flash and the gravitational wave arrival and things like that. So that's still to be tested more completely, but so far everything's checked out with Einstein's predictions.
That was my question. But
Okay.
Aaron had one.
Sorry, Dana?
Yeah, so you showed other black holes we know about, but most of those are really observed through companions, disks. So, how much is this the first time we've ever seen direct evidence of something we know is a black hole?
Right, yeah, so all of our previous measurements where people say it's a black hole, like we think that there's a black hole at the center of our galaxy that has a mass 4 million times that of the sun. But we don't directly observe that black hole. What we observe is the effect of stars. Actually, there are orbits of stars around that black hole, and it's actually from those orbits that we calculate that the mass is 4 million times the mass of the sun. But we don't really know it's a black hole. We just know it's a whole pile of mass sitting at the center of the galaxy that doesn't seem to be giving off any light, right? And those other measurements, the way we measure them in binary systems is the black hole is actually sucking gas in, say, off the other stars, and we see the X-rays. Again, we're not actually really seeing the event horizon. This measurement actually is really the first solid evidence that these are really black holes with event horizons, because that pattern of it ringing down, that's the signature of an event horizon, right? If it didn't have an event horizon, this signal just would have kept on kind of getting louder and louder, and it wouldn't have rung down. So we have basically measured, this is really the first concrete detection that these really are, the first detection that's where we can say that these really are black holes with event horizons. They aren't just some concentration of mass. It really is a black hole as described by Einstein's theory. So we have a whole paper on that. It is really see, I never doubted the other things were black holes, but it's a good point. This really is the first actual concrete observation that there are black holes in the universe, not indirect.
Based on models.
Right, the rest are based on models. This is the first time we've actually seen the wobbling of the event horizon as it, rings out. Yes?
Has anyone noted any change in the pulsar timing, pulsar frequency associated with it?
Well, pulsar timing is sensitive to waves at these way lower frequencies, right? So we're looking there for these very massive black holes that live at the center of galaxies. So we do not expect a signal like this to show up in the pulsar timing data. Interestingly, a space-based detector would see these kinds of systems much earlier in their existence. In fact, there could be tens of these in the Milky Way, depending on exactly how these black holes, but still much earlier in their existence when they're just orbiting very slowly. And a space detector would be able to detect these kind of systems much earlier in their evolution before they do that final crazy merger. So, but no, in pulsar timing, just way too low frequencies. I'll take one more question, and I think I might wrap it up to let people get out to where they need to go. Yes?
So besides confirming Einstein's theory, what else can we learn that's new from this pulse?
Well, one of the things that we've learned from this is, it seems like we've discovered a new type, a new form of black hole, much more massive. So the astrophysicists now have to try and explain how can you form black holes that are, at these larger masses. So we've already discovered a new kind of object in addition to discovering the first binary black holes. And that's what we really hope to do as we go forward in gravitational wave astronomy. It's a whole different way of being able to view the universe. It's like before, all the information we got in the universe came from light, and we were deaf. Now we can hear. So now we can pick up vibrations in the universe. There are a lot of things in the universe that put out a lot of light, like the sun, but very feeble gravitational waves. And then there's other things like merging black holes that put out maybe no light, but huge amounts of gravitational waves. So we hope to start discovering, unveiling the whole dark side of the universe. And so it's a new form of astronomy. We're going to listen to the universe now. All right. Thank you, everyone.
Actually, I'm pretty sure. Yeah, plus my face is probably pretty sure.
How are you?
Physics, or you just
What?
are you in physics? I can't